Thank you, Farshad. I'll be talking about improving accuracy of the AI model for concrete strength and reducing strength variability. So many of you, when you say about accuracy and precision, I want to give you some brief background, right? So let's say a truck came in, you broke cylinders, and you got 5,000 PSI, right? So 5,000 PSI strength is right in the middle of the bullseye, right? Okay. So now, if you're predicting this, that's not accurate or precise, right? It's all over the place, right? So that's not very good. Now, in this case, you're being very precise, but you're not accurate, right? Precisely wrong, right? You're precisely wrong because you want to be right here and you're away, okay? Here, you're kind of getting in the ballpark, but the precision is not very good, right? You're shooting a little bit not perfect. And that's perfect. That's kind of what we want, right, for an AI model. And if you want to put in numbers, you want to get to 5,000 PSI plus minus 10%. So right now, that's kind of where you want to be in the AI model. So that's where we want to get. But let's look at what you typically get in a project. These are actual project data from the same mixture. Right? So this, the first one you're seeing is a project data from Florida, non-entrant concrete, 4 months, 300 data points. So a lot of testing done, okay, almost on a daily basis, all right? You're seeing that's a variability, and let's look at the statistical numbers. Average 5210 PSI, okay? Standard deviation is 478 PSI. Now that's very good quality control according to ACI 214 committee, which is the concrete statistics committee, right? So this is very good concrete, all right? Now, one thing you want to look at is even though this is very good concrete, you got a spread of 2770 PSI is the spread, right? And that's a 5.8 times standard deviation. So you can say it in terms of the standard deviation, right? Now I'm going to get to a little bit of a more nerdy part, okay? ACI 318 building code says, in order to accept concrete, you got two requirements, right? Running average of 3 cylinders, 3 tests should be over F prime C. No single test should be 500 PSI below the specified strength, okay? Now ACI 301 takes those two equations and converts it to a target average strength that the producer needs to hit with a 1 in 100 failure probability. Right, so they got statistical equations. Now what I did is I've got the average, I got the standard deviation, I back calculated what should be my specified strength, okay, from this data. So if you do that, you find that 4570 should be my estimated specified strength, and the single test is 4070, 500 below, right, 500 below. So if you're finding that you still, even though I've designed according to ACI 301, 1 in 100, you have two instances in this 300 data points where it is below 4070 PSI, okay, below that. So you're failing, you're having low breaks, right? And there are 16 times you're failing the running average criteria. So producers don't like this, right? So even though you're designed for 301, you're still having some issues. People want to core and they want to avoid that. So what happens then is that they over-design over 301. So 301 may say this, they add an extra 200, 300 PSI because they don't want to deal with these issues, okay? And it kind of makes sense too, because if ACI 301 telling you to do 1 in 100 failure probability, you got 300 data points here, you're going to see 2 to 3 data points that are low, right? Now, the low data points in this case were only maybe 100 PSI below. Remember, it is 4070, they got 4,000, right? 3980. But some people still want to core at that, right? So that's why producers just want to over-design and get rid of the problem. Okay, so there's one thing. So that's kind of a side note, just background information. There's another project from Columbus, Ohio, air and train concrete, 7 months, 300 sets of data. Again, the results are very similar, very good quality control, 438 PSI, and the range is 6 times the standard deviation. Just keep attention to 6 times the standard deviation, that is 5.8. And there is a pattern to it, right? Makes sense. If you are familiar with statistics, normal probability distribution, 6 times standard deviation around the center, that includes about 99.7% of the data, okay, for normal probability distribution. So that makes sense that it is that range, okay? And you see that the same thing, producers are designing more conservative than 1 in 100. Now, what do we have? Our problem. So even for very good quality concrete, standard deviation of 500 psi, according to 214, right? You are expecting the actual project data range of 3,500 to 6,500 psi, plus minus total of 6 standard deviation, right? 3,000 psi is the range, so that's plus minus 30%. Okay, so that makes sense, right? So that's what you're expecting in the field, all right? So this variation is because of material, manufacturing, and testing changes during the project, right? This is happening, this is real, okay? So your AI model needs to consider all these changes in order to be accurate. Very important, okay? Now the question is, how good can it be? Can it be predict, that's the range. Now, even if it's a very accurate AI model, can it give a range of 3,000 to 7,000? Remember, the best you can get to is 3,500 to 6,500, right? That's the actual test data, right? So if you take the 3,500 PSI, the most accurate can get to is predict exactly 3,500, right? So if there's some variability in the model, it's going to be a little bit lower than 3,500. So you can expect 3,000 to 7,000, maybe a very good AI model can predict. But if that's what your prediction is going to be, if I tell you it's 3,000 to 7,000 PSI, how useful is that information, right? I mean, it's kind of useful in the sense it kind of gets you in the ballpark, and you can say, I can design my mixture, I can save some money in developing mixes and all that. But if it's such a big variation, it doesn't do anything to reduce my over designs, right? So that's very important. If I want to reduce my over design, can the AI model help reduce that variability, that 3,500 to 65, and bring it down? So that is the important part, right? So let's look at that. Where is that variability coming from? Briefly looking at material variations, a typical average concrete plant, that's 1,000 cubic yards a week, has about 12 shipments of cementitious materials, 40 of coarse aggregate and 24 of fine aggregate, okay? And remember, the material coming from the same source can lead to variability, okay? You can't say that same source, it should be perfect. No, it doesn't have to be. So ASTM C150 is there, that's a spec for cement. It's mainly for specification compliance, okay? Couple of things to remember, it is done on composite samples. So daily you take a sample and you average it, you mix it up, right? And on every 2 weeks, you may get a mill test report. But by that 2 weeks, you might have hundreds of truckloads already batched, okay? So if your AI model is built on the mill test report, it's just saying that all that 100 batches of the batch is same. The cement doesn't have any impact on it, right? So clearly that's not the case, right? So you cannot capture the cement's impact. So what is the cement's impact? So there's an old NRMCA study back in 1955, which we did, is we had 5 sources of cement and we had blends of that as well. We kept that as a control. We tested it, okay? These 5 sources of cement, we sampled every 2 weeks over a year. So over a year, you had like 26 samples, right? And the samples were batched on 5 different days. So 15 cubes over 5 days, 3 cubes a day. So we broke that about 7,000 cubes. And then we also did concrete mixes on the best, the worst, and the average. Okay? So the mortar mixes and then the concrete mixes. And see how the variability of the cement is from a single source. There's a 62 study with 14 cements where the conclusions were very similar. So I'm just going to talk about the 55 study. So those are how the results look like. Okay? Remember, 26 samples are being tested from the same source, okay? If everything tested equal, they should be flat, 100%, okay? 100% line. So clearly there's a variability. Even for the control, there is a plus minus 5%, maybe because of testing or whatnot, batch to batch variability, all that, okay? But here you see one cement here gave us minus 40% to plus 20%, okay? And then this cement was a little better. It is a minus 20 to about plus 20. So that you can see the coefficient of variations, 10% almost here, 5% here. So you seeing the cement is contributing to the motor strength variability during the course of the year, okay? So correlation between mortar and concrete is very good. This is for the different cements, and I tried to plot against the mortar strength standard deviation they reported and the 28-day concrete strength range. So there's kind of a weak relationship. You can say on average you're getting about 800 psi strength impact because of the cement shipment variability during the course of the year. About 800 psi, 28-day strength range, okay? So that's a finding from this report, okay? You got the ASTM C917 is a variability of cement from a single source. They report all these variabilities, and you can see that some cement plants are very accurate, but 200 psi standard deviation, some are like 400 psi. So there is this range. So you can say that maybe these plants are giving you more accurate compared to those in terms of concrete strength variability. Now, I don't want to just talk about cement. There are other cement SEMs too, which impact concrete strength. A similar study was done on fly ash back in the late 80s. They looked at 4 different fly ashes, 3 Fs and 1 C ashes, and they found that the strength activity index does vary. These were like about 60 shipments of fly ash from the same plant over a 6-month period. Okay, so 10 shipments every month, every 3 days they got a shipment. So they found that yes, the strength activity index varies from about 70 to about 90 here. There is a loose correlation with fineness, you can see that. This fly ash is obviously a lot more accurate. So there is that variability. All these are creating issues, okay? So, all right, so let's look at manufacturing variation. What are the manufacturing variation? Now, can AI handle manufacturing variation? Okay. Producer has a lot of data. Okay, so they got the batch tickets, the batch weights, okay. I'm pretty sure the AI model already considers the batch weights, okay, because they have the data. But then they also have a lot of other data, mixing speed and time of the truck, number of techs they have, number of technical managers, percent concrete rejected, are they doing internal audits, are they doing claims, are they using certified plants and trucks, they have labs, do they do material tests, are they doing calibrations of their equipment, are they doing internal tests? Are they running slump and all those kind of stuff at the plant? What about the truck time? So a lot of these data are being measured, right? Producers are measuring it. And clearly a lot of this data can correlate to the actual strength of the concrete, right? So we need to capture all that. And we actually, in NRMCA, we measure overall, every year publish a quality survey report on average of all the producers, okay? And there are some things that are not measured. For example, is the producer keeping the stockpile tilled, right? Uniformly graded, well graded. So mixing sequence, are they mixing it properly, right? Every time are they mixing it right way, right? And then there are things like uniformity. What about the blade wear of the truck, right? How about the truck buildup? Will that affect or mixer uniformity? So these things are not measured, but then there are best practices like the certifications of the plants and trucks can capture some of these things, right? If they're certified, it captures. So you've got to control it, right? So you cannot measure it, so AI cannot do much if you can't measure it, but you can capture it. Okay. The big thing is water, right? So you got the batch weight we can get the water from, but then there's a lot of other sources the water can come from. The water can be in the mixer drum, right? When they're washing the mixer. It can come from moisture in the aggregate, right? They can add water to the slump rack or the job site, right? So you can have a lot of various sources of water. If you have a direct measurement of water, that's great. If you don't have a direct measurement of the water, indirect measurements, slump, concrete temperature, air, all that can correlate with water, right? Delivery time, high delivery times, high air, low density of concrete. So all of that can correlate with time, right? So we need to capture all that. And the other thing is that producers also have plant operations data. Things like how old are the trucks, cubic yards per hour, like volume-wise. So all that can correlate again to the strength. So the AI model needs to effectually capture all these things. Then finally about testing, right? So there's a paper done by Professor David Richardson, Missouri. He said, how can testing variability affect strength? And he calculated everything. If you add it up, you'll be surprised that any concrete cylinders are getting any strength at all, right? Because there are so many ways concrete strength can be lower because of poor non-standard cure testing practices, right? Like for convex ends and so on and so forth. Now, there's only one way really you can increase the strength slightly if you really load it really fast, right? That's the only way. But there's a lot of things that can drop it down. So you need to capture that. The standard curing, that's a big issue too, right? If you don't cure the cylinders properly, in the field, maintaining the moisture, 60 to 80 degrees Fahrenheit, transporting to the lab within 4 hours, then curing it properly in the lab, that can have a huge impact, okay? And unfortunately, that's not done enough, okay, in our industry. That's a fact, okay? If you don't take care of the cylinders properly in the first 48 hours, you lose about 20% strength, okay? So that's, we published an article in CI a few years ago. You can take a look at it. And again, that is something that the AI model needs to capture as well, right? Testing practices. So what do we have? Even for very good quality concrete, you can have a plus minus 30% strength variation. And that's because of material manufacturing and testing. The AI model input data needs to consider all these things, okay? Needs to consider all those things. You just can't depend on batch tickets and mill test reports because they are incomplete information, right? You got to look at C917. I showed you that. SCM finance, that'll be a start, okay? But in the future, what I'm looking at is maybe we can have daily physical and chemical properties of cementitious materials. That can correlate to performance, right? So vertically integrated companies can have the data, they can use that, but in future, if I can dream, right? A batch of cement comes or SCM comes, you have a little probe, you just scan it, you get the data, chemistry, and then you can predict the strength. We are not there yet, but maybe in the future we can get there, right? Like Spock would do that, right? We'll do that in Star Trek. Okay, we talked about manufacturing testing parameters. Now, a concrete strength AI model, I have hope we can reduce variability, over design, low breaks, but you got to predict strength using daily, real-time parameters, material manufacturing testing parameters. And we need to quantify the impact of all these sorts of variability, right? And you either lower by better quality practices, you say that, hey, this is the water, this is how it is impacting, and the producer makes control, adjust for that, or they say, hey, the cement has come this way, so you can expect a low break, so the producer does something that just mixes, right? So you got to do all those kinds of things, then you can cut that variation. I'm going to take one step further and say, now you got a lot of ways you can actually estimate things like slump density air in the truck, right? There's a lot of ways. Once you make the prediction, you can refine your prediction some more based on these input parameters. Then you can get very accurate, kind of like a unified data model, right? So you can go from the whole stack. So if you're able to do that, that's great. One last thought I want to leave you with is, you also consider cement strength AI model. That's a lot more focused because cement guys have the data, they're running C917 strengths, they are having the cement physical chemical properties on a daily basis, right? If they can predict that, if you have a good model, they know the parameters they can control, there's a lot more control in a cement plant, then the cement producer can reduce the variation of cement strength and optimize for carbon footprint, which is the main focus right now, okay? So that's all I had. Thank you.
Thank you so much, Karthik.
So like a lot of focus has been on the cement variation, but remember the study was done in 1950. That's before the XRF being used. That's before a lot of automation being used. So that focus may be biased. Okay.
Yeah. Yeah. One thing is, yeah, I want to say it's not just the cement, right? All the SCMs, they all contribute to the variation. Definitely, that's one thing. Regarding the time period, though, what I would say though is that what I showed in the 917, right? So that's from the appendix of 917, right? The variation, the standard deviation of the different plants. So you do have a variation from some plants are a lot more tighter, 200 psi standard deviation. Some are more 400 psi. So you do see that. And maybe it's time to do another evaluation of the different sources. Maybe that's something we should consider and see whether it's more accurate.
Is a requirement, so we're going to do it more often, right? Yeah.
Yeah.
Thanks.
Thank you.
Karthik, maybe I'll ask a question
Sure.
as well. Very interesting information about the sources of variability. A lot of these AI models are looking at predicting performance, and strength being one of them. Do you have an opinion of how good of a prediction accuracy these models need to have as a minimum? Is it to essentially match the variability that we see in the field, the experiment? Is it okay if they go worse? Do they need to be better?
Yeah, see, I think, like I said, right, so this is good concrete, 3,500 to 6,500, like, that's good concrete, right? Very good quality concrete, actually. So the best you can get is that. If a perfect AI model which captures everything, precise, accurate, can get 3,500 to 6,500. But even that has limited use, right? I mean, it's good in the sense it helps me like mixed development purposes, it helps, right? It reduces time, cost. From that perspective, it's great. But then the real benefit is trying to reduce over designs. That I cannot get if you just predict that range, right? So the model needs to inform how we can cut that variability down, right? So maybe you got to do one step and say, where is the variability coming from? You know, if you have a good model, you should be able to give that pointers, right? Sensitivity kind of an analysis, they should be able to do that. And if they can cut that down, I think that's a great. I think we want to get to a stage where the truck comes, right? Right now we're predicting slump air and everything, that's good, they're estimating, but then you can say, hey, this truck is going to be 4,500 to 5,500 PSI. You can get to that tight range, then you really have your answer, right? You can, yeah.
So maybe in addition to these global models that people are trying to get cement from all over, at least the country, and the different producers and all that, there is a need for more localized models that look at one specific, for example, ready-mix producer, different operations, maybe different cements that they're using to just capture the variability of the data that they produce, given that they have a lot of strength data at least, or more developed data.
Yeah. The other challenge is what you will see with is that producers may have a lot of batch data, like they have thousands of mixes in their plant and all that, but they may not have all the other data, right? The cement data, the fly ash data, which is very important, right? So they need to capture a lot of that, and some of the other data may not be fully available too. Some of the other plant quality data that I showed, right? Operations data. So that may be the challenge. The data quality may be the challenge. Yeah.